Well, good day to all of you. To continue with our discussions on the first law of thermodynamics. Well, what did we do? In the last class, we had ended with the law of the statement of the first law for different systems, and we found out that usually we find out that even for closed systems, since it is very easy to maintain a constant pressure and we always prefer to perform processes under atmospheric pressure. So, therefore, we encounter constant pressure processes very frequently. So, for such processes we find that the term U plus PV usually dominates, and the same thing happens for open systems as well. As a result of which we have included the term enthalpy in our energy balance or in the first law system. Now, since enthalpy is so very important and we will be dealing with it very frequently, so before I proceed further, I would like to spend a very short while discussing the important some interesting aspects of the enthalpy of a system. Now, what is enthalpy? Basically, it is a convenient property, as you know, which combines U and PV, or in other words, it combines internal energy and the flow work. And we have seen that it has energy units, but the important question is, can we conserve enthalpy just like we have conserved energy? For isolated systems, the first law gave us the law of conservation of energy in isolated systems, right? So, in the same way, do we have something like the conservation of enthalpy? So, let us see that. Now, if you find that, suppose we have a rigid vessel where maybe it is rigid, it is immovable, and maybe an isolated system. So, therefore, there is no amount of internal energy change in it. Say for example, we have got some particular system which is enclosed by a adiabatic boundary condition. So, therefore, this vessel, it is rigid, enclosed by an adiabatic wall. And just here we have a piston cylinder sort of an arrangement. Okay, it is fully enclosed, but we have a piston cylinder type of arrangement from where we can impose a pressure P on the system. Since it is rigid, it cannot move. So, therefore, my dV equals to 0, right? And since it is enclosed by an adiabatic wall, so therefore, I know that my dQ equals to 0, fine. And since there is no other work being performed on it, so therefore, naturally my P dV equals to 0 or my dW equals to 0. So, and since it is a closed system, so naturally for this particular system I know, my du is also equal to 0. Now, I keep on increasing the pressure on the system, right. So, therefore, when I keep on increasing the pressure on the system, but since the system inside it cannot move and there is no heat transfer, so therefore, the du remains constant in the system, since dq equal to 0, dw equal to 0 holds even when I am applying pressure. So, therefore, what happens to the enthalpy change of this system? The enthalpy change is, in this particular case, my d or rather delta H, that is equal to U2 minus U1 plus P2 V2 minus P1 V1. If I write it in differential form, this is dH equals to du plus d of PV. My volume remains constant, so therefore, this becomes du plus V dP. I know my du equals to 0, but dH is not equal to 0 because dP is not equal to 0. So, therefore, what do I find? I find that even when du equals to 0, even when we find that there is no energy change of this particular system, the enthalpy of this system can increase since the pressure of this system is increasing. So, therefore, in reality we cannot have something like the conservation of enthalpy just like we have conservation of energy. Or in other words, enthalpy is not a true energy term like enthalpy is not a true energy term like energy, and enthalpy can be included in the energy balance equation for two instances which we have already shown. The first instance was for the open system which I have shown, where we were performing reversible flow processes, and the second case is non-flow processes at constant pressure, where only expansion work or volume change work is involved. So, therefore, we find that enthalpy can be included in energy balance equation for under only two circumstances, the ones for which I have derived the equations and incorporated enthalpy in my first law. Those two processes are reversible flow processes and non-flow isobaric processes, provided they are undergoing only PV type of work. And fortunately, I should tell you that majority of the industrially important processes, they fall in one or other of these two categories. So, therefore, we include enthalpy in our energy balance equation, and we usually forget that enthalpy is not a true energy in its strictest term. Now, the other thing which I was thinking of discussing before closing the chapter on first law is that we can apply first law for different closed systems, right. I give it to you as an exercise for applying first law and finding out the work interaction. For isobaric I have already done, isochoric also I have already done. For adiabatic, polytropic and isothermal processes, you can take ideal gas as the working fluid, and you can do it even for a generalized system as well. Now, whenever for these particular systems we find that there is some amount of heat interaction or there is some amount of work interaction, and that brings about a change in property of the system. The only property change which occurs due to heat interaction is usually the temperature change. Temperature change can occur both by heat interaction as well as by work interaction, but how much amount of the temperature change will occur due to some amount of heat input on the system, that depends upon the heat capacity of the system. With the same amount of heat input, different systems will not exhibit the same amount of temperature change. You are already aware of the heat capacity, but again, since it is quite a unique property, so I would like to spend some time on the heat capacity of the system. As this is very evident, you have been studying it from your school days, so you know that the heat capacity of the system is defined as the amount of heat which it absorbs and the temperature rise which occurs as a result of this heat change. For the instantaneous heat capacity, it is usually defined by this particular form. Now, there are some important things which I would like to mention. The first important thing is that heat capacity has got a meaning only when the heat input brings about a change in the temperature of the system. So, therefore, it is meaningless when phase change occurs, because under that condition it becomes infinitely large, since the heat transfer in this case does not bring about any temperature change. The other important thing and very interesting thing is that suppose due to this heat input, when there is a chemical change occurring, then we find that maybe due to the chemical change there is some amount of heat which is evolved or some amount of heat which is absorbed in. So, therefore, the heat can be absorbed for the chemical change along with increasing the temperature of the system. Now, under such conditions we find that if we try to evaluate C, and if the reaction is occurring at a very slow rate and internal equilibrium is not established, then the C which we are going to measure and the C which we are going to measure when internal equilibrium is established are going to be different. So, therefore, it is very important to note the condition under which we are measuring C, when a chemical reaction is taking place within the system, and usually it is specified that the heating here is slow enough for equilibrium to be maintained. The C which is measured under that condition is the C which we should be taking, because if the measurements are taken very fast such that before internal equilibrium is attained, we try to measure the temperature rise amount and the amount of heat which is going on, then the value of C which we will be getting will be different from the value of C which we will be getting when internal equilibrium is established and the measurement is rather the heating is very slow and internal equilibrium is established. For with the same argument, C usually refers to a closed system. And the most important fact about the heat capacity is, although it is a property of the system, it is a path dependent and it has got no meaning until the path of the heating is specified. So, therefore, for each path of heating we can have a different value of C. And the two most commonly used or particularly important kinds of heat capacity are the heat capacity at constant volume and the heat capacity at constant pressure. We find that the heat capacity at constant volume is just the rate of increase of the internal energy of the system with temperature, and the heat capacity at constant pressure, which we use much more frequently, is the rate of increase of the enthalpy with temperature. It is important to remember that this includes the flow work along with the increase in along with the increase in internal energy of the system, provided PdV is the only form of work. So, therefore, although it is a property of the system, it is path dependent. The heat capacities are extensive properties, while the molar or the mass heat capacities, they are intensive properties. Well, the next thing which I would like to mention is that so long we have been discussing about the law of conservation of energy. Now, we find that whenever a process takes place, then for that particular process the total amount of energy interaction with the surrounding is equal to the total amount of energy increase or the total amount of energy change within the system. But even while obeying this particular concept also, we find that some processes can be possible, some processes cannot be possible. For example, I take up a few processes which are shown here. Suppose for each case I would like to go from state A to state B. What is it? It is some very simple. I have two equal blocks of copper at 20 and 30 degrees centigrade. I bring the two blocks together and then each block is at 25 degrees centigrade. I can spontaneously come from state A to state B. But the reverse, I have two blocks at 25 degrees centigrade, I bring them together and then I find one block goes to 30 and the other block comes to 20 degrees centigrade, that particular process is never possible. Again, in the similar way, suppose we have some particular gas at one half of an insulated container, the phenomena of free expansion as it is called, maybe this is an insulated container. In this particular container, this portion is evacuated and here we have some particular gas at say some particular temperature T and some particular pressure P. I remove this particular partition, the gas automatically it expands and fills the entire space here. But when the gas has filled and I try to push some particular partition, the gas will automatically never come back and fill one half of the container. So, while this free expansion, this phenomena of free expansion as it is called, this is a spontaneous process, the reverse never occurs. In the same way, suppose I have one other container, again say I assume an insulated container and I have gas A here and I have gas B here. I remove this, I find that gas A and B mix together to form a homogeneous mixture. But I have to use tremendous amount of energy if I want to separate this homogeneous mixture into gas A and B, and I try to confine gas A at one portion of the partition, gas B at the other portion of the partition. It is never possible in this particular way. I can keep on citing several such examples where we find that while the process in one particular direction is possible, the process in the other direction is never possible, even when it does not flout the law of conservation of energy. In all these systems, you find that two blocks at 20 and 30 degrees centigrade and each coming to 25 degrees centigrade, the amount of the heat transfer which would have occurred, with the same amount of heat transfer, we can always postulate that two blocks at 25 degrees centigrade can be made to contact, and one comes at 20, the other goes to 30 degrees centigrade. The same amount of energy interactions in pen and paper will show you that the same amount of energy interactions can take place when we go from state A to B and when we come from state B to A. But all of us know that while state A to B is highly possible, state B to A is never possible. Now, why does it happen? Why do some particular processes are feasible while the reverse process is not feasible? Why some processes occur spontaneously and others do not occur spontaneously? At one point of time, it was thought that whenever any process it gives out heat, it is spontaneous. Whenever it has to absorb heat, it is not spontaneous. But then people found out there are several endothermic reactions as well which are spontaneous. So therefore, they felt the same way the Joule's experiment, while we could use the weight to heat the water, we could not use the thermal energy of the water in order to perform work unless we make some other arrangements, as I have discussed. So why are all these things happening? Then people found out that, well, the primary reason is that some processes are feasible and others are not feasible. For example, heat always flows from a higher temperature to a lower temperature. Never the reverse thing happens. So why are these things happening? So therefore, in order to define these things, the second law of thermodynamics has come up, and the second law of thermodynamics that postulates that heat can flow from, rather that postulates that why some processes are feasible while the reverse processes are not feasible. Well, there are two statements of the second law of thermodynamics which I will just be displaying tomorrow, but what I am going to discuss right at the moment is that while people found out that some processes are feasible, they wanted to develop or they wanted to propose a quantitative measure of why some processes are feasible, why some others are not, whether it can be quantitatively predicted, so that suppose they want to perform any particular process, they would find that particular quantity, they would be evaluating that particular quantity, and based on the results they get, they would be able to decide in which direction they should proceed. So, the second law was an attempt in this particular direction. The second law has a large number of statements. One statement is by Kelvin Planck, the other statement is by Clausius. Now, let me tell you that all these statements, they are with reference to the heat engines and the heat pumps, because mostly, as I have told you, that the oldest endeavors of man were in terms of heat engines and heat pumps. So, Kelvin Planck's statement in a nutshell, it says just the same thing which Joule had observed, that it is impossible to continuously absorb heat from, or rather to convert heat into work by working with a single reservoir. That would lead to a perpetual motion machine of a second kind, of the second kind, and if that were possible, then Joule could have performed the experiments in both the directions. And Clausius said that if heat has to be transferred from a body at lower temperature to a body at higher temperature, then work has to be done to make this particular transfer possible. right. So, these were just qualitative statements. Now, based on this, further developments were done. The first development was a Carnot cycle and the Carnot's theorem which followed from them. What was the Carnot cycle? The Carnot cycle was a reversible cycle or a reversible heat engine cycle, where Carnot had devised it in terms of a PV work of a gas contained in a cylinder. Let me tell you, Carnot cycle is just a reversible cycle comprising of two adiabats. These are the two adiabats and the two isotherms, two reversible adiabats and two reversible isotherms. It can be made to apply on any particular system performing any type of work. So, the correct representation is, instead of representing it in terms of a PV plot, it is better to represent in a plot of F and R, where F is the thermodynamic driving force, R is a thermodynamic displacement. F and R can be P and V, it can be sigma and A, it can be anything depending upon the system. Now, in this particular Carnot cycle, there was some very important theorems which he had proposed. Now, among these theorems, the first thing which he proposed is that any irreversible cycle has a efficiency much lower than a reversible cycle. So, therefore, the efficiency of a reversible cycle will be the maximum. The next thing is, for all reversible cycles operating between the same two high temperature and low temperature reservoirs, no matter whatever path they take, the efficiency of all reversible cycles will be the same irrespective of the working medium and irrespective of the processes. If they are reversible cycles, they will have the same efficiency for each and every cycle, and the efficiency will be higher as compared to a irreversible cycle. Now, based on this, they proposed that an ideal gas Carnot cycle, that means when ideal gas is used as a working substance in a Carnot cycle, then for that particular situation he found out that Q1 by Q2 equals to T1 by T2. This has been developed from the concept of efficiency of the cycle. Now, we know how to define the efficiency of a heat engine. Carnot cycle was devised for a heat engine, where in very brief, let me tell you, a heat engine is a device which takes up heat from a high temperature reservoir and transfers heat. This heat engine, it transfers heat to a low temperature reservoir and does work. It takes up heat Q1, provides rejects heat Q2 and does work with the remaining amount of energy Q1 minus Q2, right. Now, suppose we use ideal gas as the working fluid in this heat engine, then Carnot found out that Q1 by Q2 is equals to T1 by T2. Later on, Kelvin he thought, or rather it was his great intuition, he thought that why only ideal gas as the working fluid? If suppose we can devise a temperature scale with heat as the thermometric property, then definitely we should be able to propose an absolute temperature scale completely independent of the working substance, where the temperatures of the two reservoirs will be in proportion to the amount of heats taken up and rejected in them, and therefore, we should be able to produce, or rather we should be able to devise an absolute temperature scale, and this gave rise to the concept of the absolute temperature scale. Since it is outside the domain of phase equilibrium thermodynamics and I have got a limited time of just 20 hours, so therefore, I will not be going into the details of this. but you can take up any textbook and go through the definition and the development of the absolute temperature scale, right. But what is of importance to us is that based on this, we find that the very important proposition was suggested. It was that for any particular working substance, when it is performing a reversible cycle as a Carnot cycle, that means the reversible cycle comprises of 2 adiabats and 2 isotherms, then in that case we can always write down that Q1 by T1 equals to Q2 by T2, or in other words Q1 by T1 minus Q2 by T2 equals to 0. And if we remember that Q1 has been taken up, or rather heat provided to the system, so therefore it is positive. Q2 is heat rejected from the system, that is why it is negative. Then taking this sign into account, we can always write it down in this particular form, which gives us the equation as sigma Qi by T equals to 0. And if we have an irreversible Carnot cycle, then in that case what do we know? We know that the efficiency of an irreversible Carnot cycle is 1 minus Q2 by Q1, and the efficiency of a reversible Carnot cycle is 1 minus T2 by T1. So, therefore, in this particular case we know this is less than this, or in other words we can always write it down as T2 by T1, it is less than Q2 by Q1, or in other words in the same way we can write it down as Qi by T sigma, this is less than 0. So, therefore, in any particular working substance operating in a Carnot cycle, we find that sigma Qi by T is less than equal to 0 for a Carnot cycle where the equality sign is applicable for the reversible process and the inequality sign is applicable for a irreversible process. Now, next we also know that any particular cyclic process plotted on a FR plot, that can be broken down into a series of Carnot cycle. I am not going into the details of all this because I assume that you know the basics of thermodynamics, or you can find it out in any particular textbook of thermodynamics. For any particular process, we can break it down into an adiabatic process, an isothermal process and another, an isothermal process, an adiabatic process and another isothermal process, and we can bring the adiabats as close as possible because they are never going to intersect with one another, and therefore any reversible cycle can be broken down into a series of Carnot cycles, and for each of the Carnot cycle this particular equation holds if it is a reversible cycle, and this particular equation holds if it is an irreversible cycle. So, for any particular reversible cyclic process, we can always write down this is equal to 0, and for any particular irreversible process, we can always write down this is less than 0. So, combining the two, we can always write down dq by t for any particular cyclic process, it is less than equal to 0, which is another consequence of the Carnot's theorem, and this was first proposed by Clausius, and it is known as the Clausius inequality. And from here stems out the criteria for feasibility of different processes, which we will be discussing in the next class, where I will be introducing the concept of entropy and we will be discussing the feasibility of the different processes. Just like I had introduced internal energy and enthalpy from the first law, I will be introducing entropy from the second law, and once we have introduced this, we have understood the energy interactions and the energy change of different systems. We can understand when some processes are feasible and why some processes are not feasible on a quantitative manner. After that, we go into the depths of phase equilibrium thermodynamics. As I have already mentioned earlier, first we will be dealing with single phase, single component, the simplest type of systems. We can also deal with single phase multi-component systems where the composition does not change as the process proceeds. So, both of them will have the same treatment and we are going to deal with them. Then we are going to deal with single component two phase systems, then multi component two phase or multi phase systems. So, with this I end up this particular class. Thank you very much.